always trick one or two students with that. And the main reason, again, is reducing this energy, because it's very easy. We've established just opening up the lattice at that temperature is easy. When you're looking at the step, now you have shear involved, so you're involving deformation. It takes energy, and you try to minimize that. And you can get into a condition where it's going to be cleavage like this, there's another cleavage like this, and there's going to be cleavage at an angle in between, as opposed to being really a tearing step. So this is all what's happening if you are at very cold temperature. Now we're going to what happens, just another view of it. It shows going from one grain to the other. Say I had the perfect orientation. The first grain here that cracked only had one line with a step right where the arrow is, but when I get to the other grain, it's a different orientation, and now I need to reorganize my cracking into multiple cracks that will evolve and converge a little bit. So I had a few images of those. Okay, high temperature. We are forming voids, and it's not something that comes straight up of this equation. If it was just for von Mises, we will keep deforming and deforming and deforming. Eventually, you have small particles, inclusions, or grain boundaries. There are a lot of pieces in the microstructure where you're going to start forming small voids. And depending on the quality and the purity of your metal, these voids will form earlier or later. If you have more stresses, if you're looking at a high strength material, they will form it earlier because your stress is higher when you start deforming. And also we call these dimples. That's the opposite, essentially. Complete opposite way of breaking here. When I see that, if I go to microscope and I see that, I can't really say that that the material didn't provide the capacity it was supposed to provide, because I can see that it's stretched. What you see as white here is a high profile, and if I was to look on a cut view of this, it will look somewhere like this, where I have these broken ligaments. So I have a void, and then I have the ligament. That's the white portion because it's got a lot of profile here. And then the grayer or darker portion is the bottom of the hole. So I know that I had to go through all this process and forming these stretches before I broke. So it's very hard to argue any effect of a notch here, because that specific area broke even without knowing that there was another one right here. So it's not even going from one side to the other. It's sort of working its way internally, and then eventually the crack will come right through it. So that's dimple, and you can have them in tension, you can have them in shear as well. These are tension because you can see all around it. If the break was happening this way, they wouldn't look all that round with the nice profile around them. It's kind of just a way to explain how you go from forming a little void around a particle to these stretch voids that eventually form the fracture. So this is more or less of an introduction for tomorrow, where you see the effect of the individual grains here. So that's another type of fracture that is relatively common. It can be hydrogen embrittlement. There are other ways you can also make the steel at risk for breaking through the grain boundaries, but it's not the more prevalent way. The more prevalent way by far is to form these dimples. And there are other ways. So I was looking here at some cross-sectional view here, and you can see the crack is going up and down to go around grains, or sometimes it's inside the grains. And these are very slow, low ductility or slow cracking mechanism that we're going to talk about in more details tomorrow. But it gives you some idea that this nice, as soon as you go away from the normal ductile process, you can start thinking about for tomorrow that now the effect of the microstructure is going to be very important. If you have large grains, if you have small grains, If you have the time for chemicals in the environment, chlorides, to penetrate into the crack, that's also going to affect the deformation in there and how easy or hard it is to open up further. So I hope that you get a sense about the fracture surfaces with these crack propagation lines. It's diverging in a ductile behavior. The one exception is when you have a brittle behavior at very low temperature, and we talked about the reasons for those differences. We have cleavage, dimples, and the other one that I've talked about today is intergranular fracture. If it's due to hydrogen embrittlement, if you have too much hydrogen in your material, it's essentially working on the capacity side here, how much energy it takes to form new surfaces. The hydrogen just very rapidly gets localized in the high stress regions, and it's helping the separation. So it's one of those few situations where you're actually affecting how easy it is to crack. And it's one of those conditions where you can have hydrogen embrittlement, a very brittle fracture without any deformation at ambient temperature. It only happens in relatively high strength steels, though. So, to some extent, the regular structural steel, if you control the impurities and you're not exposed to super low temperature, just ambient, and you're not in the North Pole or something like that, that's the reason why we don't have to worry too much about the mechanics here, because everything is fine. But as soon as you start going to a higher strength, now you become more at risk for every sorts of effect, embrittlement, effect of the environment in terms of stress cracking, which we're going to talk about next class. So if you're building a car, a lot of what I've talked about today is not all that useful. You want to still worry about our dollar sign here. And you're not too worried about fracturing other than when you're forming the steel, which is still very important. So you have to control those conditions. But so I hope that was a good overview, although it's a lot. I've done this and I've been taught this stuff forever. So it's a challenge for me to bring it down in topics. But I welcome questions or comments, and we'll take it from here tomorrow. Fracture fatigue, yeah, it's 3:35, and we're going to do it this spring, actually. It's me and another principal scientist. It used to be Professor Suresh's class. He was our dean of engineering a couple of years ago. It's a lot of theory, but it's useful. Oh, yeah. Well, yeah, I'm probably going to have to go and move on to the slow cracking for tomorrow, but we can definitely talk about it in more details. Yes? No, it's going to be way too brittle. It will shatter like glass, if you keep lowering the temperature. And it depends your exact temperature in the range. I'm more familiar with liquid nitrogen type temperature for experiments, and you're limited to typically stainless steel, austenitic stainless steel, not all stainless steel, and aluminums. And the colder you go, even with these materials, you have to worry about notch effects. So it's hard. It's hard to apply high loads on the material at cold temperature because it's hard to move the dislocations in those conditions. All right. Thank you.